designed to review for you the contents of Module 1 in my AP Environmental Science class. This module included what is environmental science, a review of the scientific method, understanding ecosystem services and worldviews, and a general understanding of physics and economics. Here is a list of essential vocabulary that you need in order to understand the contents of this unit. This essential vocabulary is broken down into the major components that you need for understanding the scientific method, the ways in which we make environmental decisions, and what systems look like. So you should be familiar with the difference between a prediction and a hypothesis, be able to explain what a worldview is, and identify them. Talk about the differences between preservation and conservation. Describe the idea of the tragedy of the commons and give examples. And in terms of economics, you should be able to describe full cost pricing, what a cost-benefit analysis is, and the difference between indirect, direct, hidden, or market costs. It's important to note that a hidden cost is also sometimes referred to as an external cost or an externality. For our purposes, they are synonymous terms. As it comes to systems, you should be able to identify the difference between a closed system and an open system. For the parts, you should be able to talk about inputs, outputs, flows, also known as throughputs, stores, and sinks. Not only should you be able to identify them, but you should be able to explain how they function and provide examples. You should also know what thermodynamics is and be able to explain the first and second laws, and then talk about work and efficiency in terms of physics and those laws. Before we really dig into things, let's talk about planetary boundaries. When we talk about AP Environmental Science and what environmental science can do for us, we're not necessarily talking about saving the planet. As Mr. Anderson indicates in one of his videos, we're really talking about saving our society. When we talk about saving our society, we have to talk about our impact on our environment. And that impact is measured by a variety of planetary boundaries. As you see here in this image, there are several different planetary boundaries that we should be concerned about. Those are circled in green. The ones we should be concerned about are the climate crisis, our overloading of the nitrogen cycle, and biodiversity loss. We should also note that the phosphorus cycle, deforestation, and ocean acidification are moving closer to reaching their boundary, meaning that the Earth will no longer be able to sustain the way that they are functioning now. Please keep in mind as we move through this discussion that we're talking about how humans have overloaded these natural systems, what we've done to do this, and how we can fix that problem. Let's clearly make a distinction between what is environmental science and what is environmentalism. They are two separate things that are often conflated with one another. Environmentalism is a social and political movement that includes lobbying, personal and public activism, and increased education for awareness. Environmental science, however, is a combination of different scientific disciplines that we use in order to understand our impact on our Earth and the ways in which our society can become more sustainable in the future. Environmental science is incredibly interdisciplinary. It includes information from a variety of different disciplines. We're talking about biology, chemistry, physics, political science, economics, anthropology, sociology, and if we really want to get specific, we're talking linguistics too. How do we refer to our planet and the things that we have done to it? You could also include English and journalism and media studies. How do we actually talk about and share the information that we have? Let's talk now about the scientific method. This is something you've been doing since you were in 3rd grade. You know how to ask a question, design a simple experiment, and get an answer. But when we talk about college scientific experiments and moving on into the real world of research, the scientific method becomes a little more complicated. There are more steps that need to be taken in order to ensure that you're getting accurate results. While this may look linear, it's important to remember that this process is actually cyclical. You're going to often return to previous pieces in order to make sure that you have done your due diligence in figuring out if your answers are actually accurate. The scientific method generally starts with observations and questions. There's something you want to know. Most scientists will then do background research. It doesn't do any good to waste research grant money and your time trying to answer a question that's already pretty definitively been answered. Additionally, that background information will help you design a more specific experiment and a more specific hypothesis and prediction. After you've done your background research, you construct your hypothesis. A hypothesis, remember, is just an explanation of how or why something occurs. It tells us the big picture. What are the phenomena that we're looking at? The hypothesis should not be a statement that's immediately testable, and it should look at the relationship between two variables. When you construct your hypothesis, you may also include a prediction. This is talking about the very specific things that you are doing in your experiment and the response you expect to see. Typically, it is talking about, if I change my independent variable in this way, I expect to see this result from my dependent variable. After you've constructed your hypothesis and prediction, you design and carry out your experiment. You analyze your data, and then you decide whether your response is supportive or rejecting of your hypothesis. If it rejects your hypothesis, perhaps you go back and refine it. You retest. You change your model of experimentation. Just because you get an unconfirmed response doesn't necessarily mean that you did things incorrectly. This is why repetition is important. The more repeated an experiment is, the more accurate the data becomes, and the more certain we can be of the response that we get. Professional scientists and educators will publish their findings in peer-reviewed journals, and others in their discipline will attempt to replicate their responses. Here are some important terms you need to know in terms of the scientific method. Understand the idea between a theory and a law. A scientific theory is something that has been tested multiple times with multiple different hypotheses, and they have all come to the same conclusion. For example, we talk about the unified theory of evolution. This comes from multiple different experiments over hundreds of years that have shown that the ideas first put forward by Darwin were essentially correct, with some modifications once we learned about DNA and inheritance laws. A law is something typically only associated with physics, and in some cases biology. Laws are things that define how our physical universe occurs, and they always occur the same way under the conditions that they are set in. The law of gravity, for example, the law of independent assortment. These are things that we will consistently see under the conditions in which they were studied. It is very difficult for something to become a law, and most often those are associated with the things that are the physical world around us, rather than individual characteristics. We've already talked about the difference between a hypothesis and a prediction. Make sure that you are clear on that. A hypothesis is a broad explanation of how or why something happens. A prediction is specifically associated with the experiment you are conducting and talks about how the changes in independent variables will lead to changes in dependent variables. Speaking of variables, there are 4 different types that you should be familiar with when you're talking about research. You have independent and dependent variables. These are the ones that you're studying. Your independent variable is what is modified. Your dependent variable is what you measure. How does the changing of your independent variable affect the response of your dependent variable? You also have external variables. These are things that you can't control about your research. If you're doing an experiment outside, external variables may be changes in temperature, wind, cloud cover. And then you have constant variables. These are things that are designed to be exactly the same throughout all of the parts of the research. This is to ensure that when you're actually looking at your relationship between independent and dependent variables, you're actually seeing the relationship that exists, not something that is what we call confounded or confused by other things. You will also have different kinds of groups in experiments. Most often, you have an experimental and a control group. The experimental group is one that's treated with the independent variable in order to determine whether there is a response of the dependent variable. Your control group is kept the same. It does not interact with the independent variable at all. Please note it is possible to have multiple controls and multiple experimental groups in a particular research. Lastly, when making conclusions, you have to talk about things in terms of causation or correlation. Most often, research is going to be talking about correlation. It's more likely than not that X occurs with Y in this pattern. But we can't definitively say that every time X occurs, Y will also occur. In order to have a clear causation response, you have to have a very tightly controlled experiment, and that's almost always impossible. You have to do it in a laboratory setting where everything is controlled. And typically, those kinds of experiments don't translate well to the way the real world works. Also, when you're talking about your hypothesis and your conclusions, you talk about things in terms of support or reject. It is impossible for science to prove anything. There's always a potential chance that new research and new technology could overturn the things that we previously thought were correct. Although we do our due diligence and we do our research as impeccably and detailed as possible, there is always that very slight chance that we could be incorrect. Okay, so we've talked about what environmental science is and what it isn't, and how we use the scientific method to answer questions related to environmental science. One of the things that it's important to note is that every individual is going to approach environmental problems in a specific way. And that way is defined as their worldview. How do they look at society and the environment around them? The way in which they look at that is going to strongly determine the kinds of choices that they make and the kind of research decisions or policy decisions that they undertake. Worldviews can typically be divided into two large categories. These large categories are talking about what is the center point of their worldview. If the center point of their worldview is actually the global environment itself, we call this a geocentric worldview or an ecocentric worldview. The specific way that we talk about that is what's called the Earth Wisdom worldview. However, if an individual decides that humans and human society are the important piece, they typically have what's called a planetary management worldview. This typically puts humans at the top of the pyramid and says that because we have the capability to control the world around us, then we should. Underneath each of these big categories, there are actually some sub-ideas or sub-schools. Let's go back to environmental wisdom and talk about the pieces that are attached to that. Earth wisdom typically works under two ideas. The first of them is the idea of land ethic. Land ethic comes from the book Sand County Almanac by Aldo Leopold. Leopold talked about how we are part of nature. We are part of this larger ecosystem, and it's important for us to behave that way. Land ethic is also termed the golden rule of the environmentalist. Only do to the earth what you would do to yourself, because whatever you do to it is going to affect you somehow. In addition to the idea of land ethic, you also have this idea of preservation. To preserve something means to keep it as close to normal and pristine as possible. Don't touch it. Preservation was championed by this man named John Muir. Muir also created the Sierra Club, and is responsible for one of the greatest environmental debates in the early 20th century. He fought Teddy Roosevelt over whether or not there should be a dam put in the Hetch Hetchy Valley in Yosemite National Park. Unfortunately, he lost, but his argument spawned this idea of preservation, and it pushes some of the major policies that some of our governmental agencies take even today. So that's Earth wisdom. Let's talk about the sub-pieces of planetary management. Let's talk about them in terms of worst to best. Probably the worst one we can think about is the no problem school. The no problem school says that technology will be able to fix any problem that we have. We can figure out a way to fix it from within the system with a tech fix. The problem is, it's really hard to fix something when you're inside the system itself. And technology often introduces a whole host of its own problems that actually make the problem worse rather than better. Also underneath this is Earth as a spaceship. This tells us that if we can understand how the interlocking pieces of the Earth work, we can control them. The problem is that one system tinkering with it often has cascading effects with others. It's not really plausible to think of the Earth as a machine, because it doesn't work that way. Probably the best one is what we call stewardship. Stewardship tells us that because we have the ability to maintain and control our ecosystem, we should. Sometimes stewardship is tied in with this idea of conservation. Conservation was championed by Gifford Pinchot, who is also one of the first heads of the U.S. Forest Service and worked really closely with Teddy Roosevelt, and had a pretty heated debate with his former classmate John Muir. Conservation says that you can use resources, but you must use them in a way that they will remain sustainable over long periods of time. Use enough now, but make sure there's enough to continue into future generations. One of the things that's important to understand is how events in environmental history have shaped the way that we view environmental issues today. If you review the timeline that was given to you at the very beginning of the school year, it's important to know some important events. The disasters that are listed in all capital letters are important for you to know. You should know where they occurred and what the major effect was. So, for example, you should know what happened at Love Canal and the fact that the CERCLA or Superfund law was passed in response to that. Also note that the Gulf of Mexico is synonymous with the BP oil spill. All of your disasters are listed by location, not necessarily by the commonly known name. Additionally, Prince William Sound is the running aground of the Exxon Valdez tanker. It's also important to know some people that made a big impact on the way that we view environmental issues. Teddy Roosevelt is responsible for our National Park Service and our National Forest Service. He was a strong believer in Gifford Pinchot's idea of conservation, and he passed the Pure Food and Drug Act. Jimmy Carter created the Department of Energy, protected a vast amount of public land. He was president and signed into law the CERCLA or Superfund law that protected us in terms of environmental disaster cleanup. Richard Nixon created the Environmental Protection Agency, and he was one of the first presidents to recognize Earth Day. Rachel Carson is a scientist and author who wrote Silent Spring, which is a deep dive into the effects of DDT, which used to be a pesticide. It's important to note with Rachel Carson that while a lot of her research is relatively sound, there is some research coming out that the effects weren't necessarily as bad as she portrayed them to be. John Muir, as we've discussed, was the champion of preservation, and he's the founder of the Sierra Club. Gifford Pinchot was the head of the Forest Service under Teddy Roosevelt, and he was the one who really championed this idea of conservation. Lastly, we have Garrett Hardin, who wrote two very important pieces of philosophy of environmentalism that we need to think about. He wrote the idea of lifeboat ethics, which talked about if you have a limited amount of resources and only a few extra places to use those, how do you decide who gets access to resources and who's left out? And he also wrote the idea of the tragedy of the commons. Remember, a commons is an area that everyone shares together, but no one person or group is responsible for maintaining. Individuals choose to overuse the commons, thinking that their use doesn't really affect everybody else. When in fact, if one person overuses a resource, others are likely to do the same, leading to a long-term loss of a resource for the entire group. In short, tragedy of the commons says that individual short-term gains lead to long-term collective losses. In addition to understanding what environmental science is and isn't, how we use the scientific method, history, and worldviews to shape the way that we make decisions, we also have to think about it in terms of economics. Economics is a driving force behind our society as it shapes our growth and our development. This is why we have to take economics into account when we make environmental decisions. The important thing to do first is to identify how we use economics to identify values of things. So let's take a step back in time and go back to your civics and economics class and review a couple terms. When we're talking about economics, we have to think about supply and demand. What do we have available to sell or to produce? And how much do people want it? If people want more than there is, the price is going to go up. If they want less than there is, the price is going to go down. So we have to think about this in terms of surplus and deficit, which can also make a big impact on the price of things. There are a couple different kinds of costs that we need to keep in mind. The first one is a direct cost. A direct cost is associated with what is immediately included in the production, typically raw materials. An indirect cost is what is necessary for production, but doesn't go immediately into the actual product. This can be the manufacturer having to pay maintenance workers to fix their machinery, or rent on their building and electricity. Then you have hidden costs, which are also called external or externalities. These are associated with the use, production, and transportation of the product, but aren't necessarily included in the price you pay. These can include air pollution, water pollution, and healthcare costs for things like carbon dioxide and atmospheric issues that cause asthma. These three values, direct, indirect, and hidden, work together to give us this idea of market cost versus full cost. The market cost is made up of all of the indirect costs, plus the direct costs, plus the profit that the company wants to make. Full cost, however, is something we can use to make sure that people understand the impact of the materials and services that they're buying. Full cost pricing includes everything in market cost, so the indirect, direct, and profit, but it also adds in the hidden costs or the externalities. This makes the price of purchase of a material or of a service representative of its impact and the amount of money that it's going to take to mitigate the damage that product causes. When we talk about development, we typically talk about economics in terms of GDP, GNP, GPI, and per capita GDP. Let's kind of unpack those and see what those terms actually tell us. GDP is what we call gross domestic product. This includes the value of all of the products and services that are consumed within one country. So this would be in the borders of the United States, for example. Gross national product is a little bit bigger. It includes everything in the GDP, but also the production and consumption of materials from this country in other countries. So this may include everything in the United States, plus how people in the UK consume American products. The GPI is a new way that has been indicated to really measure whether or not a country is considered developing or developed. and GPI is called the Genuine Progress Indicator. This measures economic development in a country, which is often a more accurate reflection of its progress through demographic transition and its development into a fully developed country. We also talk about things per capita, which is a Latin phrase meaning per person or per head. So per capita GDP means the GDP value for each person in a population. You can figure that out by taking the total GDP and dividing it by the total population. This can give you a decent idea of how much individuals make and how much the value of the resources are worth for an individual person in the population. There's also this thing called the IPAT equation, and we use it to measure the impact of a population, its technology use, and its consumption. In the IPAT equation, I equals impact. And impact is equal to population times affluence times technology. In this equation, affluence is equal to consumption per person, and technology is equal to emissions per consumption. Universally, developed countries have a much higher IPAT value than those that are developing countries. Economics also allows us to figure out how can we make environmental decisions by placing a monetary value on the things that the world does for us. We use this thing called a cost-benefit analysis. It's basically a fancy term for saying a pro-con list. We identify what are the costs of taking an action and what are the benefits of taking an action. If the costs outweigh the benefits, we typically choose not to do it. However, if the costs are lower than the benefits, we get more benefit out of it, then we're likely to do it. When we talk about costs here, we're not just talking about monetary value. We're also talking about time, environmental degradation, and impact on future populations. When we talk about outcome, we're not just talking about profit. We're talking about economic growth, jobs, cleanliness of an environment, the ability for populations in the future to have more resources than we have now. So we take those cost-benefit analyses and those things that we learned about in terms of market and full cost pricing, and we apply economics to environmental decisions. We do that by this thing called economic services or ecosystem services. Ecosystem services are ways in which we can place a monetary value on the actions of an ecosystem. And there are 4 types of ecosystem services: provisioning, supporting, regulating, and cultural. These ecosystem services all do a job for the animals and plants that live on this planet besides us, but we can also figure out how much monetarily are we gaining by using these resources. Provisioning services actually provide something that we can take away or that we can use and that will provide us with a monetary value. This can be, for example, taking timber from a forest in order to be able to build a house or to make furniture to sell it. Supporting services are those that make it possible for an ecosystem to support life. Supporting services include the formation of soil and your biogeochemical cycles. Regulating services are those that maintain quality, and the best example of this is photosynthesis. Photosynthesis removes carbon dioxide from the atmosphere, which can help to improve air quality and regulate climate change. And then you have cultural services. Cultural services are those that are more individual, historical, and perhaps even religious in nature. It's going out to a park and sitting and enjoying the world around you. It's going to a national monument. It's going to a national park. Often there are strong group ties to a cultural location, which allows us to get a benefit from it. So it's not just enough to think about economics and make them a part of our decisions. We have to think about solutions that tie in economics to incentivize people to make more environmentally sustainable decisions. Some of the possible solutions that people use today are subsidies for sustainable corporations. If a corporation is taking the steps to make their products or their services or their actions more sustainable and more environmentally friendly, governments can choose to give them a subsidy, which is we actually pay them extra money to do these good things. We may also provide them with tax breaks. We charge them less in their payroll or employment taxes so that they can put that money toward being more sustainable and continuing their efforts. We can also put taxes on those who aren't sustainable, and those taxes can sometimes come in the form of a carbon tax, charged per kilogram of CO2 released into the atmosphere, or higher tariffs. It's going to cost more money for you to ship your product somewhere else because it doesn't follow these environmentally sustainable rules we've set. And also, we can use consumer activism and education. If individuals know where their products are coming from, they can be more likely to make more informed and environmentally sustainable decisions. Lastly, we have our physics. And when we talk about physics here, we're talking about systems and thermodynamics. So let's take a quick look at what these pieces are. So there are 3 types of systems that you should be familiar with, but only 2 of them exist actually in nature. Open systems allow both energy and matter to enter and exit the boundaries of the system. Closed systems allow both energy and matter to enter, but only energy leaves. And then an isolated system doesn't allow anything in or out. As far as we know, the only naturally occurring isolated system is our universe. But of course, quantum mechanics and string theory might quickly tell us that we are actually incorrect on that one. When it comes to open systems, natural ecosystems tend to be a great example. Energy and material flow in and out freely, moving through those parts of the ecosystem to provide it with resources or materials for new things. The Earth is a great example of a closed system because matter from space and energy from the sun can enter our world, but matter under its own power typically doesn't leave. We as humans have to make a big change in order to get that matter to leave. And usually it's burning tons and tons of gasoline on the far end of a rocket. So now let's talk about the parts of a system. Systems are made of 5 basic pieces: an input, an output, a flow, a store, and a sink. The input is simply what comes in. The output, what goes out. The flow is the series of cycles or changes that the inputs go through in order to become the outputs. An example of this would be a biogeochemical cycle. Within the system, there is this thing called a store. This is where you hold matter or energy for use later on within the boundary of the system. Outside the system, there is this thing called a sink. These are places where the matter or energy is stored outside the boundaries of the system. And almost exclusively, your sinks are going to be the atmosphere, your oceans, or your soil and rock. Lastly, let's talk about some of the major concepts in physics that are important for us to understand as we move forward in learning about how energy and matter move through ecosystems and how we as humans use energy resources. Work is a term that's going to be important as we move through energy. Remember that work equals force plus distance. This means that work is only done if the force applied, which is our energy input, is actually used to move something. If something isn't moved, there was no work done. When we talk about energy, we have to think about the 2 different types of energy: kinetic and potential energy. Remember that kinetic energy is energy in motion, and potential energy is energy stored, either through chemical bonds or physical location at a height. It's also important for us to remember that energy obeys 2 basic laws, and those are the laws of thermodynamics. Remember from our discussion of terminology that thermo means heat, dynamo means movement, and the suffix ic means the process of. So thermodynamics is the process of moving heat. The first law of thermodynamics is also known as the law of conservation of energy, and it says that energy is neither created nor destroyed. It can only change forms. This means we can't lose energy, but we can't gain any new energy either. The second law of thermodynamics is sometimes called the 10% rule. The law actually states that the total amount of usable energy in a system is always decreasing. The simpler version of this is no energy conversion is 100% efficient. This means that as energy changes from one form to another, some of it is always going to be lost as waste heat that can never be recovered. A general rule of thumb for this law of thermodynamics is the 10% rule. Only 10% of usable energy is transferred in each conversion. This will become important when we learn about efficiency and also when we talk about the movement of energy through ecosystems and population pyramids.